Hello friends and welcome back. In this video we'll be talking about calculating moments of inertia so general rules to calculate the moment of inertia and some special cases that you may be interested in knowing, or at least knowing where to find the information about, and a couple tricks and theorems that can help us along the way if we need to do some specific calculations. Now, first off, so let's repeat the definition of moment of inertia and see where we say where we're at. So we said the moment of inertia I for a system of particles is defined as this combination. So the sum of the masses mi and the distance squared to the axis of rotation. But for, so let's write it down. For a system of particles. For an extended object, instead, sort of a continuous object, let's write it here, continuous object. Typically what you want to do is write an integral instead of still the product of the little mass elements, dm, and times r squared, the distance of this specific, the little mass element from the axis of rotation. This integral looks a little confusing. There's few characters, but it can be a little tricky to deal with. And so something that helps a lot is when we consider cases where the object is, for example, basically a one-dimensional object. Examples are maybe like a thin straw, or a thin stick, rather. Thin stick is a better definition. Like, I don't know, a drumstick or a spaghetti or something like that, where the thickness in these two dimensions is completely negligible when I compare it to the length. And I don't know, a hula hoop, for example, is the same thing, or a ring. And in this case, what helps often is to write dm, so a little mass element. See, what is the mass of this tiny fraction of this object? Well, I can write it as lambda times dx, where dx is the physical size of this little element, and lambda is called linear mass density. So the mass that is contained in this little portion of this ring is lambda times dx. Most often we will use lambda and other extensions that I'll talk about just now as constants, but in principle the density could change from point to point. But at least it's a little more, it looks a bit more natural now to put this inside your integral, so that I can integrate from, for example, from 0 to 2 pi r. I integrate from 0 to the whole circumference of the ring, and in order to find the moment of inertia. Okay. Now, if my object, instead of being one-dimensional, is a 2D object, like a spherical shell, or a slab, a thin sheet of paper, or something of this sort, then typically what I write is dm as sigma times dA. dA is the area element, the surface element, and sigma is, as you can probably imagine, is called surface mass density. And then the task is to integrate this quantity. And last but not least, let me zoom out a bit, is the case where I have a 3D object. So the most general situation of you know, the potato that I drew, or a bean just now, or obviously exact shapes, solids like a cube or a sphere, like a full, not a hollow cube, but a full cube, etc. Then what I write is dm as rho times d volume, meaning that, again, a little volume element in this object has a mass that is proportional to that element times the density in that place. And this is the volume or just mass density. Volume mass density or just mass density. All right. You may be happy to hear that in this course we won't be doing a lot of crazy integrals just for the sake of it. This is not a calculus course. However, those of you that are interested in calculus and like the topic, and you can challenge yourselves with, you know, pick your favorite geometrical shape and see if you can calculate the moment of inertia around a certain axis that you choose. And in general, we will do, however, a couple exercises because it's nice to do something like that at least once in your lives, but nothing too crazy, don't worry. In practical cases, what you do oftentimes is to look at tables of moments of inertia for interesting or you know, common shapes. And these, for example, include, I'll draw just a couple examples, but you can find many more and they're really interesting. Let's say I'm going to draw some axes of rotation as best I can, and then I'll put some objects rotating in these axes. Take, for example, a loop, as I said, like a thin ring that is rotating around the geometrical a loop or a hoop also. The moment of inertia is just the total mass times r squared, where r is the radius of this circumference and the total mass of the hoop is there. So it's precisely sort of has the same shape as the definition. And that's something that I can expect, but that's interesting to know. Second case that I want to point out, well, I mentioned the thin drumstick or spaghetti. So a thin cylinder, the moment of inertia of the cylinder is, as it turns out, 1/12 of, but not turning around this axis, my bad. This is just 1/2 mr squared, where r is the radius of the cross section of the cylinder. And so interestingly, see, it depends on r and not the length of the cylinder. See, it doesn't if it's rotating around this axis. However, and this is interesting also to point out again, the same object, a thin uniform cylinder, but if it's rotating around, I deleted one too many. If it's rotating around this axis, so it's sort of like as you would twirl a drumstick and not roll it, then the moment of inertia in this case is that 1/12 that I was telling you about. 1/12 what? M times, check this out, L squared, where this is L. See, it's really interesting to see that the same expression or the same formula can give you completely different results, and not only different results, but different dependencies on the various properties of geometrical properties of this shape, depending on the choice of rotation axis. So it's very important, interesting to know. What else? I can choose to spin a sphere, for example, around sort of an axis that goes through its center of mass. So for a sphere, a full sphere, the moment of inertia is, for example, it's 2/5. mr squared. Let me rewrite this 5. But interestingly enough, for a spherical shell, I don't know how to draw it. Let's just write it. Spherical shell, the moment of inertia is not 2/5, but it's 2/3 of mr squared. And again, the denominator really is not my forte right now. So again, it might seem maybe counterintuitive or a little surprising, but it takes a different amount of the rotational inertia, and we will talk briefly, well, not briefly, we'll talk about what that means more in a deeper manner shortly enough, is different for a hollow sphere and in general for a hollow solid than it is for a full solid of the same mass and the same geometry. So very interesting. What else? Maybe I think I covered some of the main examples, but you can find tables on most respectable textbooks, and I'm sure online there's many of other common shapes like a slab or a cube or what have you of these values. I promised some theorems and some tricks that can help us doing the calculations and speed them up. And well, let me get to a new page, and then I'll show you what I mean. So let's write down some theorems and tricks. Some theorems and tricks. All right. Now, trick number 1 or theorem number 1 is called the parallel axis theorem. This theorem says the following, that if you take my potato and let's say that I know what the moment of inertia is around the center of mass of this potato. And I'm wondering, well, I wonder if I instead have this potato rotate around this axis instead, can I relate the values of the rotational inertia in these two cases? And the answer is yes, you can. And so if this distance is d between the two axes, and mind you, parallel between the two, then the moment of inertia I is the moment of inertia about the center of mass plus md squared. All right? So, for example, we had the previous slides or the previous page, you learned, I don't know, for example, that twirling a drumstick around its center of mass, the moment of inertia was 1/12 m length squared. If you were to rotate this drumstick about a point that is not the center of mass, but it's parallel to it at a certain distance, then I would have to add md squared. So it's not exactly a twirling, but this whole thing is rotating around it like this. Okay. All right. Parallel axis theorem. This is really, really helpful because then you basically need to calculate the moment of inertia once around the center of mass, and then for every parallel axis to the one you used once, you can just add this simple combination, and that's the moment of inertia. Nice. Theorem number 2 is the perpendicular axis theorem. Perpendicular axis theorem. Maybe not as useful, but equally interesting at least. And this says it's got a slightly more limited application because it requires a flat object, so a thin pancake type thing. And what the perpendicular axis theorem says is that if you know the let me draw it in dashed actually. If you know the moment of inertia around two perpendicular axes on the, let's call them conveniently x and y. So if I know x, and now I'll not tease the moment of inertia for rotations around x. So rotations around this axis and rotations around y, like this, then I magically know the moment of inertia around a third axis that is perpendicular to both of them. So both x and y must be perpendicular, and z is perpendicular to the plane in which the pancake lies. And notice that I could have chosen x and y sort of at any position, as long as they're perpendicular. And as it turns out, the moment of inertia about the z-axis, the perpendicular axis, is actually the sum of the two moments of inertia. How cool is that? Really, really interesting. And this is the perpendicular axis theorem. Let's zoom out to make some room. Hope you can still see most of it. Otherwise, rewind the video and go and check it again. Trick number 3, let's write it here. It's called a stretch rule. Stretch rule. And the stretch rule is as follows. If you have an object, let's say, well, for simplicity, I'll draw it like a cylinder, and you know its rotational inertia around a certain axis. And if you take this object and you keep everything the same, but simply elongate it, or actually even compress it, to be fair, you change its length along the axis of rotation. Okay, so along the axis of rotation, with the total mass being the same. So you're essentially redistributing mass, redistributing the mass in a proportionate way to the stretching. Then this second moment of inertia is actually identical to the first moment of inertia. All right. And you can probably, if you think of the formula that defines the moment of inertia, you've got the same amount of mass at the same distance as before, just more spread out in one case, or less spread out, but proportionally so. And so it's, in the end, the product of mr² is the same, because I'm summing the same things. So the two are the same. This is why, for example, remember the moment of inertia of the rolling spaghetti. The moment of inertia of the rolling spaghetti was 1/2, was it? mr². See, it's independent of the length of the spaghetti. As long as the mass is the same and the radius is the same, there's no dependence on the length. This is precisely a kind of a manifestation of the stretch rule at work. Okay. Let's squeeze this. Now, last but not least, trick number 4, which is arguably the least utilized. Maybe that's unfair. No, that's not true. But anyway, it's called it's the additivity. I don't know if this is the official name. I don't know if it has an official name, but it's essentially the fact that the total moment of inertia of a system of objects is simply the sum of the individual moments of inertia. And so if you have, let's say, I don't know, a cube like this, and a slightly taller parallelepiped like this, and you know I1 and I2, then let's say that if you glue them together in an even taller object, then the total moment of inertia is simply the sum of the two. And this interestingly works even in reverse for interesting shapes. One example that I want to give you is this, where let's say that I ask you to calculate the moment of inertia of, let's do it in yellow, of, I don't know, like a disk that has another disk cut out of it. So it's full here, and there's a hole there. Imagining to have to do an integral for this, it's a bit of a nightmare, right? Or at least it is for me. But what I can do is, well, I know the moment of inertia of the big disk, okay? Let's say that I've zoomed out. So this is the big one. I know the moment of inertia of the smaller disk. Let's call it I1 and I2. Then the moment of inertia of this object here is the first one minus the second one, right? Because I can remove them, or because if I add the smaller disk to this final shape that I'm interested in, I find precisely I1, right? So you can find the moments of inertia really interesting and complex shapes by using a clever combination of simpler shapes with known moments of inertia, and you're happy, you're good to go. Very, very interesting. All right, this was it for this video. Thank you so much for watching, and I'll see you soon.